Today, we will be going over the first chapter, the first section, modeling by differential equations. So it's almost like an introduction to differential equation. What is differential equation and why do we need them? I think it's better for us to see some examples from real life so you can see the application of differential equation is actually everywhere. So, of course, we want to study them. Example 1. Let's assume you have a region. Okay, and you got a group of people, I would say like 200 people. Initially, they move into this region. Let's assume they have unlimited resource, so they don't start to kill each other. And there is no maximum capacity of the environment. As long as you have a population which is growing, they can grow to infinity if necessary. Now, under some very simple assumptions, we can do a simple model to try to model what's going on with the population. So, let's assume that the population here, which are people, have a constant birth rate, which is 0.1. That means out of 100 people, continuously, 10 newborns will be born. And then let's also assume they have a constant death rate, which is 0.05. From here you can see, okay, if it's constant, then they have a constant growth rate which is positive, which is the birth rate minus the death rate. So it's gonna be a growth at a rate of 0.1 minus 0.05. Note, this is actually the percentage. So it's not like a fixed number of person per time. It's more about like fixed percentage of person per time. How many really depends on the current population. All right. With that in mind, our goal is find the formula or the function of the population. Y as a function of t, where t is a time measured in a certain unit. It can be years, it can be month, and the rate here has to be changed corresponding to the time period. But either way. Okay, so let's see how we set it up. Number 1, we do have y to be the population. Then y prime is going to be the growth or the decay, the changing rate of the population. Okay. Now you can see the changing rate of the population, which is growing, is proportional to the current population at a rate of the birth rate minus the death rate, which is 0.05. So let's put it here. So this will be the equation that the population has to satisfy. Moreover, y at time 0 should equals 200 because the initial value also should matter. If you start with 2,000 people, of course you are going to change in a different way. All right. With that in mind, can you solve it? Then you need to ask yourself, do you know a function that if you take the derivative, it's basically the same function times a constant? To get rid of the disturbance from the constant, what we can do is we can assume the constant is 1 and try to see, do you have any hint which function satisfies this? And clearly it's e to the x. Now our next job is try to make a 0.04, a 0.5. After several attempts, I think it's not hard to see. This one will satisfy. If you don't believe it, y prime is going to be 0.05 e to the 0.05 through the chain rule, okay, which is 0.05 times y itself. Okay, so this will be the only function that satisfies this differential equation. And then what we have here is we're going to put a constant, because anything like that actually is also going to satisfy this. But now, using this information, y0 equals 200, we can figure out this is the only one that will satisfy what's going on. That's it. That's the first example of differential equation we use to solve real-life problems. From here, you should know several things. Number one, what do you mean by differential equation? That is going to be an equation which involves derivatives. In this case, you have the first derivative, but certainly you can have second, third, or even higher derivatives. Maybe in order to fix the to solve the differential equation, what we did here is we guessed the answer. Later, we probably need a better way to solve general differential equations. We cannot simply just guess every single one. When things get complicated, it's impossible to guess. Number 3, when you solve differential equations, what you are going to have is going to be some constants that is unfixed. The reason is quite simple. When you know the tangent rate, when you know the derivative, if you take the integration to find the original function, you have to take a plus c when you do the integration. That's usually where the constant comes from. So in order to fix what the constant is, you need some additional conditions. Usually it's called initial condition. Okay? So that's the first example of modeling population. Let's give it a name. We call this exponential growth model, which is probably the simplest. It is useful already, but hopefully we can do better. How do you do better? Well, go back and try to see what's going on here. You had some assumption, right? You assume constant birth rate, you assume constant death rate. Also, you assume there is unlimited resource. To make the whole thing more realistic, I think the first thing I want to do is I want to remove this unlimited resource thing and give you a second situation. Remove unlimited resource. This time, we actually give limited resource. The easiest way to give a limited resource is you simply give you a environment capacity. Okay, let's say 5,000 people. That means your population may grow exponentially to all you like because you have a constant and birth and death rate. But this time, you're not going to have a constant birth and death rate anymore. As you have more and more people, your growth should slow down, and eventually you cannot hit the 5,000 capacity. You should be always below that. Okay. So how do you rewrite or adjust this differential equation? Let's say birth rate and death rate. Okay. Now if you think about it, what you can do is you can still take the same thing without the limit, and then you adjust it by a limit using this term. Okay, so what's going on here? Well, when y is small, this one is almost like this one, times 1 minus 0, which is just 1. So this is almost exponential growth. That means if you're far away from hitting the capacity, you're basically going to grow exponentially, like before. Okay, y equals e to the 0.05 t, roughly. But now what you have is, when y is close to 1, you will have something y prime almost like 0.05 y, 1 minus 1, which is almost 0. That means when you hit the capacity, you basically don't grow, you stop growing. Okay. And anywhere in between, you can see as your y becomes bigger, your growth rate becomes smaller because this whole number becomes smaller. So that is better than what we had before, which is still simple. Okay? So this is a very, very nice equation. This is called the logistic growth. Model. Okay? And the general form takes y prime equals ky 1 minus y over n. Here k is the growth rate, 0.05, the birth rate minus the death rate. And if it's negative, it's decay. And n is the maximum capacity, in our case 5,000, so we can put 5,000 here. Capacity. Okay. How to solve it? Well, you can try and guess, Before we basically guessed something times itself with a constant if you take the derivative, but this time it's going to be impossible to guess. So I will just write down, actually let's save it for later. It's in 1.2. Okay, we will solve it later. It's going to be way more complicated than what we had before. Okay, but now to let you see the example, let's use computer programming. Let's take the first one for exponential growth. Y prime equals ky with the initial condition. We start with 200 people. We grow with 0.05. Okay, and then we just grow it for how long? For 100 points. So yep, for 100. From 0 to 20. You can see it's exponential growth. If we grow a little bit longer to let you see from 0 to 50, maybe use more points. Okay, you can see the exponential trend with a 0.05. We can also actually let this one decay. That means your birth rate is less than the death rate. So we can have a negative, maybe 0.2. So people are actually dying. Okay, you can see it's an exponential decay. Okay, very easy. Now what we want to do is we still have the ky. Actually, there is a y here. But then we adjust it with, okay, a 1 minus y divided by the capacity. So like we said before, let's pick 5,000 to be our capacity. Let's pick 200 to be where we start with. Let's scroll at 0.3 to let you see it quicker. 0.05 is going to happen, but it's going to take longer. Okay, and then we go from 0 to 50. Let's see what's going to happen. You start from 200, you keep growing. At first, you are very like exponential growth. But now what's going on? You keep growing until you actually almost hit 5,000, and the whole thing become almost not changing. The same reason we analyzed it before. Therefore, this one stopped at 5,000 and never hit it. So you can see 5,000 is actually a horizontal asymptote of what's going on. That must mean that as you have more and more populations, for example, you're hitting 4,900, which is very close to 5,000, your whole thing needs to slow down. People need to kill each other, or they need to stop giving birth to newborns in order to maintain this capacity. You can play with it later, but I will just play with several things. Number one, you can play with the changing rate. Like I said, if you change from 0.3 to 0.1, you can imagine the same pattern will happen, but it's going to happen slower. Okay, you still haven't been there until you actually do a little bit more time. You can see that thing is going to hit. And also what you can do is you can change it. What if you start as 7,000 compared to 5,000? You start with more than the capacity. Now you can see the whole thing become a decay, even though you grow. But you have to have a negative growth at the beginning because you already are beyond the 5,000 capacity. Reflecting on the former, what you can see is when y is big, this 1 minus y over n. So let me write it here. Some note. When y is bigger than n, 1 minus y over n is less than 0. The whole thing here is bigger than 1 now. Then the whole y prime is going to be negative. So beautifully, this one actually included all the possible cases. You start below the capacity, you start above the capacity. The same model can actually model it. So that's nice. This also showed you another way of solving differential equations when you have trouble. That is, you can solve it with a computer, okay, which we call solving it numerically. Most of the time, most of the cases in real life, the differential equation will be way too difficult to solve by hand. Therefore, we almost always turn to softwares to solve this. A third example, we will call it the predator and the prey. This time you have something more fancy. Not only you have one variable, but you actually have two variables. You have two populations growing together. Let's take rabbit, and we denote it by R. I would use F to denote fox population. And we know they are going to interact each other. Okay. Number one, the rabbit is going to grow naturally. when they eat grass. So they grow exponentially if there's no fox. The fox is going to die because they don't have any food if they're alone. But if you put them together, the rabbit is going to grow, and then the fox is going to capture them, and instead, so they will grow, and it will slow down the death rate of the natural death rate of fox because now they have food. Okay, so what you have will be a system of differential equations involving at least two. This is the first one, and this is the second one. Okay, here R and F are the population, are the variables. Alpha, beta. I shouldn't use beta. This is delta. Okay, so here alpha is actually the growth rate of rabbit. So it's exponential growth. But then you have to adjust by how fast the rabbit is dying because they were captured by the fox. So R times F simply says the more fox, the faster, and the more rabbit, the faster that the fox can capture a rabbit, because you basically increase the density of both species in a certain area. So beta is basically the capture. That's due to capture. Similarly, gamma is going to be the death rate. If there's no food, the fox dies exponentially. And then somehow you go against that by providing food you captured from the rabbit. So this will be the growth due to food, basically captured by the rabbit. The rabbit captured by the fox. Okay. So this is the interesting differential equation system. What we can do is we can, again, simulate it in a computer. We just take this differential equations here. We start with alpha equals 0.1, which is the growth rate. We start with beta, which is the capture, and gamma is going to be 0.2 times 0.2, so it's 0.04 death rate. And finally, captured food supplies for fox. And finally, we have a gamma, which is a decay rate for the fox. We run it from 0 to 400. We do 2,000 points. So from here, you can see what's happening is the rabbits first grow without control until a certain point. The fox start to eat them, and then the rabbits start to die really quickly. Okay. Now, when the fox becomes super small, the rabbit is almost growing like there's no fox anymore. Then they grow exponentially again. Okay, so just keep repeating this kind of periodic behaviors until they have a stability. Then after that, you have a very stable supply of rabbit, and you also have a very stable supplies of fox, and they go back and forth. Okay, so this is called differential equations. Differential system of differential equations when you put multiple of them together. This can be done, and this is useful. You can think about putting 3 or 4 or 5 species into the same places and model each one of them with the natural growth and death, as well as the interactions between different species. It's going to be complicated, and from here you can see it's useful. Okay, the last thing, we have the harmonic oscillator, which is again another very important model in real life. It comes from vibrations. So for the simplest case, you basically take an object with a spring attached to the wall. Okay, so spring, object, and attached to the wall. Okay. You assume there are smooth surface. Therefore, there's no friction. At first, you keep everything at relaxed, so the thing is just going to stay there. But now you can imagine what's going to happen if you just stretch this thing a little bit to here. Hold it and let it go. If you let it go, according to our real life experience, this one is going to shake back to here. But it will not stop at the relaxed position because you still have speed, so you need to go a little bit further. And the springs start to push you. And then slowly you slow down, and then you go back. But then you don't stop here, you keep going. And then again, the springs start to pull you until you slow down. So you just go back and forth, back and forth, back and forth, back and forth, back and forth. So you are going to have oscillation according to our experience. Now let's see how do we model this phenomena using a differential equation and how that thing matches our observations. From here you can see, well, I will let y time be the displacement from the relaxed position. So basically I'm going to say, hey, if you start with this and at here you have no force because everything is relaxed, my y is going to be how much you moved to the right or the left. For simplicity, let's just say the center of mass. This is your y at time of t. From here you can see yt is changing as you're shaking. Okay. Then y prime t is going to be the derivative of the displacement. It's going to be the velocity of the object. Y prime prime t is going to be the acceleration of the object. Now, you know, for set up a motion, we go to Newton's second law, which is ma equals f, and you already have your acceleration because your ma is nothing but my prime prime. Okay? And remember, when you set everything up, you want to set everything up in terms of y, so you can solve for y later. All right. Second, what is F? Well, what force do you have here? The force is coming from the spring force. For spring force, we go to the Hooke's law, which is F equals negative k times y. Okay. So what do you have? Number one, your force is provided by this spring. So how big is the force? Number one depends on k, which is the spring constant, which basically tells you how strong the spring is. If k is big, that means if you just stretch that thing a little bit, you are going to have a very big force. And if the spring is really loose, then you are going to have a small spring constant. Second, it's proportional to y. What do you mean by that? That means the spring is going to give you a bigger force the further you stretch it. So if you just move this one a little bit, well, you are going to have a force, but only a few. But if you stretch that thing to here, you are going to have a very strong force that the spring want to pull you back. Of course, all the assumptions are based on that your displacement is relatively small. If it's big enough, you may break the spring forever. So this one won't apply. So it's settled. The bigger the displacement, the stronger the spring, the bigger the force. Matches. Now, what do you mean by negative? That simply tells you the direction of the force is in the opposite direction of your displacement. So if you go to this way to the right, the force is going to stretch you back. And if you push everything to here, the spring is actually going to go against you to pull you to push you back. Okay? So it's basically the negative sign here is to try to tell you the direction of the force is in the opposite direction of your displacement. All right. So if we set down everything, ma equals f, then change to m, y prime prime equals negative k, y. Well, if we change it a little bit, it's going to be y prime prime equals negative k over m times a y, where this is nothing but a constant. That's the differential equation. And if you solve it, you will be able to actually model what's going on with the real motion of your y. Now, can you solve it? For this one, again, the only thing we know now is guessing. We need to guess. Okay, so how do we do that? Well, the constant is disturbing. Let's set it to be 1 and see what's going on. Do you know a function that if you take the derivative for twice and nothing become itself with a negative sign? That is going to be sine t. If you take the derivative, it's cosine t. If you take the derivative again, it's going to be negative sine t. Okay, from here you can see sine t satisfies that. Okay, wait a second. What about cosine t? Cosine t, take the derivative, negative sine t. Take the derivative again, negative cosine t. Cosine t also satisfies that. Not to mention, actually, if you multiply constant here and here, they also satisfy that. Okay, but now it's great. Why? Like we said, for common sense, if you release your hand, that thing is going to shake, it's going to vibrate, it's going to go back and forth. These two solutions, no matter which one you take, they do have the property. Okay. Now the only thing you need to think about is just how do you add in this k over m? Well, you need to think about how do you produce a number outside sine x. If you take the derivative, you will have sine 2x. By the chain rule, you have a 2. If you take the derivative again, 2 cosine 2x, you have 2 and another 2 coming from the second derivative, and then sine 2x with a negative. That's what you want. From here, you can see you do have a number here. If initially you have a number here, and this number here is going to be the square of the number here in order to produce whatever number here. Therefore, and you can check by yourself, the real solution should be y equals this. You take the derivative for twice, you have the square root of k over m for twice, then the square root cancel each other. Okay. Technically, you also have another one. And maybe all the possible linear combinations of these two. But how do you pick which one again? Like we said, when you provide people with a differential equation, it's not enough. And the reason is because when you take the integration, you will have a plus c. And for second derivative, you need to do this for twice. You probably have two constants here. So you need additional conditions to tell you, okay, which solution you should pick. You probably want to tell people the initial displacement. Like before you release your hand, where this is. You just need to tell people at time 0 where this is. And then maybe the initial velocity. But that's for later. All right. That's nice. So, very simple example. K equals 0.5, M equals 8. Start with 10 away from the real position. Do it for 50 seconds. You can see the displacement just go like that. Meanwhile, your velocity is kind of smaller, but still it's a sine cosine thing, which is no surprising. All right. So that's the 4 models we introduced for the basic differential equations. From here, you can already see it's very, very useful. Actually, naturally, in real life, when you try to model some motion, you need to tell people where it is, which is your y, and also you need to tell people what's the changing rate. And for motions, you actually need to tell people what's the acceleration. That's how you set up everything. So derivatives naturally is buried in all kinds of relationships in real life. Therefore, it's not surprising that you will see equations involving derivatives. Later, we will introduce every single models and how to do the details for every single one, how to do them by hand and how to do them by computers. But for now, I think that's enough. Okay, now we know it's very important. Let's talk about what do we need to know about differential equations. The first one is definition. Okay, basically it's just equations involving derivatives. Mathematical representation is going to be you have some kind of relationships between y prime, y prime prime, all the way to y to the nth derivative equals 0. Maybe adding another one, which is t, the time, equals 0. So it's an equation which involves everything about y all the way up to the nth order derivatives. Okay. Now the second thing we want to talk about will be the classification. Like how many different type of differential equations are you looking at? Or let's say, when the first time you see a differential equation, which part should you pay attention to know roughly what you're dealing with? Again, very briefly, the first important feature about differential equation is going to be the order. And that equals the highest order of derivative. For example, y prime equals ky, 1 minus y over n, like we said, logistic. This is the first order differential equation. When I say first order, I basically look at the derivatives and see, hey, only the first derivative is involved. The harmonic oscillator is a second order differential equations. And you can write down anything like y to the 4. Let's see. Y prime 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 plus 3y prime prime plus y prime square equals 4y. And you can see this is the fourth order differential equations. Okay. The general principle is the higher the order, the more difficult. It's very easy to think about. Basically, when you try to solve it, you have to take integration for multiple times. Okay. The higher the order, the more integrations you have to take. Second, you want to differentiate between linear and nonlinear differential equations. Linear basically means all the derivatives has a linear relationship. For example, y prime plus y prime prime minus 3y prime 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 equals 4. Linear. What do you mean by nonlinear? That's when you have y prime square. It's clearly not a linear term. Plus y prime times y prime prime, okay, equals sine y. This is nonlinear. Not only nonlinear, highly nonlinear. From here, you can see the logistic. From here, you can see the logistic growth is nonlinear. Why? Because if you put these two together, it's basically y squared. Okay? One confusion people may have, just keep in mind, linear and nonlinear is strictly referring to y. So if you have y prime plus y prime prime equals t squared plus cosine t. This part is nonlinear, but nonlinear with respect to t. So therefore, this one is still linear, because every time we talk about linear ODE and nonlinear ODE, we specifically are talking about y. And the y prime, of course, and the y prime prime. All right. In general, linear is easy. Nonlinear is difficult and usually impossible. So most of our energies will be focused on how to solve linear differential equations, which involves a lot of linear algebra. Then, if you see nonlinear systems in real life, the first thing you want to do is you want to somehow locally change it to a linear system. And then you can solve it with a linear system. Now finally, for the hardest one, which you cannot convert locally to a linear system, that's when you have to be very careful and you need to do it case by case. We can only do a few cases that we know. In general, it's difficult or impossible. Number 3, we can have differential equations. Or we can have differential systems. The predator and the prey is clearly multiple differential equations involved together, and they have interactions. So basically, the difference between these two are very easy to see. Do you have a single variable? Do you have a single equation? Or do you have multiple variables involving multiple equations? Autonomous and non-autonomous. Okay. I will just give you first order differential equation examples. A first order differential equation is called autonomous if y prime can be written as a function of y. For example, this is autonomous. Okay. Now, a general differential equation is going to be non-autonomous. And check the difference. The difference is your derivative not only depends on yourself, but also depends on the current time t. Okay. Or maybe t squared, whatever. So let's just call it gt. Yeah, it's an example. Let's just call it t squared. Okay. So what's the difference? Well, you can think about this. The change in rate basically tells you where are you going to go next, right? And then where are you going to go next only depends on where you are right now. Only depends on your current state. So it's almost like you have a robot, you have a self-driving car or whatever, okay? And you set up a lot of planning. It's just like, if you see this, do that. If you see this, do that, okay? And you do not take any feedback from the environment. No feedback from the environment. You just look at yourself. Okay? But for non-autonomous, you do receive feedbacks from the environment. For example, at the beginning, when you're in a location, according to your decision rule, you should turn left. But meanwhile, there is a wind blowing from the west, which come in at this time, which you didn't anticipate. So that's almost like some input from the environment you need to consider, not just yourself. Okay, so this is actually feedback received from the environment. That's why we call it non-autonomous. That's the difference. And later we will see the autonomous one is of course easier. The non-autonomous one is going to be harder because it depends on the time. Okay. All right. So that's roughly how we are. Oh, and let's do other types. Those types we will not do in our class. We will just briefly mention it. Okay. The first one is going to be partial differential equations. We said differential equation actually involves derivatives. Partial differential equation, of course, involves partial derivatives. Some famous ones are heat equation. ut equals uxx for one dimension. From here, you can see your u is going to be a function of time and location. So if you think about, okay, on a bar, on a heated bar, number one, at different time, at a different location, if you fix a location at different time, the bar is going to cool down. But even if for the same time, at different locations of the bar, you're going to have different temperatures. Okay, so this is going to be the heat equation, which has to involve multiple variables, therefore partial differential equations, because you have partial derivatives. Okay, diffusion, let's just do wave equations. Okay, again, one-dimensional examples. Actually, this one has constant here, this one has constant here. Things that we don't talk about. Just to let you see some examples. So that's the first type. To differentiate them, usually we say partial differential equation, which is PDE. P stands for partial. And everything we deal with in our class is called ODE, which is ordinary differential equations. So later, if I refer to ODE, basically I'm saying the same thing as differential equations with regular derivatives, not partial derivative. Okay, so that's number A. A lot of things in physics are actually partial differential equations. Things in biology usually is more likely to be ODE, but not strictly speaking. Second, you have stochastic differential equations. So not only you have a differential equation, your derivative also depends on some random effect. I will just call it randomness. So one thing you can think about is actually, the stock price. Well, if it's a differential equation, you solve it, it's going to be very smooth. This is how the stock price is going to change. But in real life, there are some randomness every day that you cannot predict. So the real thing will look like something like that. And anything look fuzzy like that, because you have a lot of randomness included, it's involved in the stochastic differential equations. So it's not surprising that you will see those kind of things called SDE in finance a lot. And also, if you think about, the trajectory of a robot, a Roomba. Okay. Nicely, your trajectory should be like this, but usually it's like this. Because number one, you have some randomness from the environment. Maybe the floor is not smooth. Maybe there's a wind. Maybe there is even a pet coming towards you, which just hit you, with its palm. So randomness can happen. Or maybe there is just some defect randomness in your gadget. It's like sometimes your motor that just doesn't run smoothly. Okay, so that's what we use for to quantify randomness in differential equations. The third one is, of course, it's a special type of partial differential equation, which we call Schrödinger's equation, okay, which is widely used in quantum mechanics. Okay, this phi can be this phi can be a vector, okay, something like that. Okay, from here you can see there is the differential equation. It's a differential equation because the derivative of phi is involved. This H here can be a matrix. It also can be partial derivatives. Therefore, it can be ODE or part PDE. But either way, this is very useful in quantum mechanics. So finally, a special type of thing called control problem, which is again very useful in real life. Okay, so basically, if you have the differential equation, this whole thing is going to grow exponentially. Okay, now what you can do is you can actually add in some control. You say, hey, if I let it be, the whole thing is going to be a disaster. It's going to hit this much number at time 20 years. But what I really want to do is I want to start to control the population a little bit such that this one got delayed to a year that I want. I want it to be after 40, 50 years. So this is what will happen naturally. This is what you want. So what you can do is you can manually add in some terms, okay, to control the dynamics such that it will achieve some result that you want instead of happening naturally. And for control problem, what you're trying to do is you're trying to design this, which is called the control. You're trying to see what kind of function that I can add to the whole dynamics in order to change the dynamic to the direction that I want. Okay, so that will be the classification of all kinds of differential equations. You have a lot of kinds. We will focus on the first ones, and for the fifth, which has multiple other cases, I will probably give you some reference in the end if you're interested in particularly some of them. Okay. All right. Now we know all kinds of differential equations. The third one we want to talk about is the initial value problem. Okay, that here is quite easy. y prime equals ky. You solve that, what's your solution? Your solution is going to be e to the kt with a constant. Why? Because you take the antiderivative, you are supposed to have a plus c from your integration. That's where it comes from. Okay. Now, how do you fix this plus c? Well, you simply just add one more condition. Usually we call it initial condition because it's usually given at phi 0. Like the y0 equals 200 we said before. Okay. Once you have this condition, okay, the differential equation becomes uniquely solvable. Basically means there's no constant that can vary. Okay, so an initial value problem has two parts. The first part is going to be a differential equation. Let's just call ODE. Something look like this. For first order, of course. Okay, and then it's not enough because your answer is not unique. You may have some constant which can vary, and the multiple solutions satisfies the same differential equation. So the second part is going to be an initial condition to help you basically fix the constant. In this case, y0 equals y0 for some y0 measurement. Okay. Everything in real life, if you try to apply ODE, will be in the format of differential initial value problem. A differential equation is not complete. You need more conditions. You need the initial conditions. You need to go ahead and measure the initial conditions if necessary. Okay? The idea is quite simple. It's as simple as the antiderivatives problems you saw before. It's like y prime equals 2x. With that information, you only know y equals x squared plus c. But then if you give one more example, that is y0 equals 3, then automatically you know y equals. So how do you use this 3? You basically use that thing to figure out what this c is. For differential equation, it's the same idea. Okay? So now, of course, we just did the first order one. In order to solve this one, like we said, you have to take integration for twice. You will have two constant. One from the going from the second derivative to the first derivative, you take the integration for once, one constant. You do it for another time to get the original one, another constant. Therefore, for this one, you probably need two initial conditions. Usually, it's given by y0 and y prime 0. Okay. Judging by physics, you need to give you my initial displacement. You also need to give my initial velocity. Okay. Think about every examples you have done before in physics. Okay. If you're trying to use Newton's second law, not only you have the law, you need to know the initial displacement and you need to know the initial velocity. Otherwise, the whole thing is not complete. Okay. From here, you can see the number of initial condition depends on the number of derivatives you have. Okay. All right. That will be the second thing. Finally, the third thing. That is solving differential equations. Okay. Number one, what do you mean by the solution? Okay. A solution of a differential equation is simply a function that you can plug in the position of y and you can calculate the derivative of y prime such that the equation holds. I think that's pretty easy to understand. Okay. But you do have two types. And the first one is called general solution. Example, y prime equals ky. The general solution is y equals c e k t. Why? Because number one, if I plug in c e k t, it does satisfy the differential equation. That is y prime equals ky. Okay? Second, c can be any constant. So how many solutions are there? You have infinitely many. Okay, that's why we call it the general solution. Okay. Now to have a specific solution, or let's say a unique solution, you need to add in initial values. Okay, so what kind of solutions do you have really depends on, are you solving the differential equation or are you solving an initial value problem? For differential equation, the only thing you can do is you can find a general solution, which involves a lot of constants, if necessary. But if you're solving an initial value problem, you will always get a unique, not always, okay? But we prefer to get a unique solution. All right. Second, how do you solve it? 3 different ways. The first way is analytically. Okay. Like the e to the x, we basically guessed it. For the logistic, maybe we have some techniques, okay? But basically it's solving it by hand. Like we solve equation. Maybe you can divide. Maybe you can take the integral, but everything is just by manual computation. So solve it by hand, okay? In general, this only works for very, very, very easy ones, or very, very specific. Which means in general, solving a random differential equation is just impossible. It's impossible to solve it by hand. All right. Then what's the alternative? The alternative is solve it numerically, which means you do it by computer. Okay. Then several things to keep in mind. Number 1, this is the most of the cases we do it in this way. So it's very common to see this. Okay. Second, it's technically not the solution. It's the approximation. Later when we introduce the method, you will understand what I mean. But basically, if you notice how I solved all these things, I actually picked the computer to tell it how many points do I want. I can solve the differential equation with 5 points. And you can see it's very bad. So in general, the more points you pick, the better. If you solve it with 50 points, it's going to be so much more accurate. Okay, 500 points, even better. 5,000 points, even better. 5 million points, it's going to be fantastic. But then you start to see the problem. Then when is it perfect? That's when you pick infinitely many points, which is impossible. Okay, so from here you can see you can always have an approximation, but it's finite. And as long as it's finite, it's not accurate. Usually, the more the better. But then there's a lot of things you need to worry about. The first one is convergence. What you're trying to do is you're trying to take a limited process, 5 points, 10 points, 50 points. Okay? Keep going, and eventually, does that thing converge? Does that thing converge to the right answer? So that's the first problem. Does it converge? Okay. Second is how to program. That involves how to design and how to program the whole thing. Number 3, you do have multiple ways of programming the same thing. Which one is better? So you need to worry about the efficiency and the accuracy of your algorithm. Maybe you have something super easy to code, but it takes 50 years to converge for a single problem. It's going to be a disaster. Okay, maybe it takes 1 million computers to perform the computation, then it's a disaster. You want something that you only use a little bit of resource and can compute a thing in really short time. Okay, but sometimes depending on the scale and the complexity of the problem, this is impossible. For example, if you're trying to do the weather, which probably involves at least hundreds of variables, which involves, if you try to do it from the Ice Age, or maybe even just for 100 years, maybe involves a lot of points. It would take forever for your computer, for your algorithm to converge if you have a bad design. Okay? So that's something you want to think about. The third thing is going to be qualitatively. For this one, we don't care too much about how the solution looks like. We just care about rough ideas. We care about the trend. Okay, we care about the equilibrium, which we will introduce later. We care about the stability of the equilibrium, and such. So instead of solving the thing to actually see it, which is maybe in this case impossible, we turn to qualitative analysis to tell people, well, it's roughly increasing. It's going to be increasing for 500 years. Okay, and the final value is going to be between 20,000 and 50,000. So we only give people some qualitative analysis. As long as it's useful, we can stop there. Okay. Ideally, we should be able to solve it. That would be perfect. You will know what's going to happen from now to then and everything in between. But sometimes the qualitative analysis is good enough. Meanwhile, maybe qualitative analysis is the only thing we can do. We can actually perform. All right. That will serve as an introduction for all the... Oh, I forgot. That's too bad. When I was writing, did I? Well, I don't know when did I switch back to the code. Probably solving it numerically, so you didn't miss much. But if you see I was keep talking, I was writing on my iPad, but I didn't switch back to the iPad screen. Use your best judgment. I think you only missed like 3 or 4 minutes, so I think that's fine. All right, that will be the first lecture.